Hello everyone. Welcome to my channel. I'm Balaji Chandrasekharan. Today, I'll be discussing about a brief overview of the system design and its insights. System design is the process of defining the architecture, components, modules, interfaces, and data for a system to satisfy specified requirements. It is the process of identifying, creating, and designing systems that meet a company's or organization's specific objectives and expectations. Systems design is more about system analysis, architectural patterns, APIs, design patterns, and gluing it all together than it is about coding. This is where all the pieces, code design, schema design, applied scalability principles, product decisions, come together. It encompasses various aspects such as scalability, reliability, availability, performance, security, and maintainability. Because our application will be able to handle the architectural load, designing our system adequately for the requirements of your application will eliminate unnecessary costs and maintenance efforts, as well as provide a better experience for your end users. Here are some of the objectives of systems design. Practicality: we need a system that should be targeting the set of audiences that is the users corresponding to which they are designing. Accuracy: system design should be designed in such a way it fulfills nearly all requirements around which it is designed, be it functional or non-functional requirements. Completeness: system design should meet all user requirements. Efficient: the system design should be such that it should not overuse, surpassing the cost of resources, nor underuse, as it will by now we know will result in low throughput output and less response time, that is latency. Reliability: the system design should be in proximity to a failure-free environment for a certain period of time. Optimization: time and space are just likely what we do for code chunks for individual components to work in a system. System design should be adaptable with time as per different user needs of customers, which we know will keep on changing on time. The best example is the well-known firm, Nokia. Now we are going to discuss some of the major components of the system design in brief. Load balancers are the most crucial component for scalability, availability, and performance measures for systems. They are a crucial component in distributed systems and network architecture, serving to distribute incoming network traffic across multiple servers or resources. They play a significant role in improving the performance, reliability, and scalability of web applications and services. Load balancers distribute incoming traffic across multiple servers or resources based on predefined algorithms and enable horizontal scaling. They enhance the availability of services by detecting and routing traffic away from unhealthy or failed servers. Load balancers can offload SSL/TLS encryption and decryption, relieving backend servers from this resource-intensive task. Key value stores are a type of NoSQL database that stores data as a collection of key value pairs. Each key is unique and associated with a corresponding value, similar to how data is stored in a dictionary or hash table. Key value stores have a simple data model consisting of keys and their associated values. Key value stores are designed for high performance and low latency, optimized for fast read and write operations. Key value stores have minimal overhead compared to traditional relational databases, making them lightweight and efficient for storing and accessing data. They are commonly used in web applications, content delivery networks, CDNs, and distributed systems. Popular key value stores include Redis, MEMC8, Amazon DynamoDB, Apache Cassandra, and Ryuk. Each of these systems has its own strengths and trade-offs in terms of performance, scalability, consistency, and features. Blob stands for binary large objects, as the name suggests is storage for unstructured data as binary objects, such as images, videos, documents, logs, backups, and other types of files. It is optimized for storing unstructured data, which doesn't fit neatly into traditional relational databases or structured data formats. Blob storage systems provide high durability for stored data, prioritize high availability, typically cost-effective compared to other storage options. Blob storage systems provide mechanisms for controlling access to stored data, including authentication, authorization, and access policies. Blob storage systems typically support different types of blobs, including block blobs, append blobs, and page blobs. Popular blob storage services include Amazon Simple Storage Service, S3, Microsoft Azure Blob Storage, Google Cloud Storage, and DigitalOcean Spaces. Databases are organized collection of data so that they can be easily accessed and modified. They are organized collections of structured data, typically stored electronically in a computer system. They are essential components of modern information systems, providing mechanisms for storing, managing, and retrieving data efficiently. Relational databases are the most common type of database, based on the relational model introduced by Edgar Codd, and they organize data into tables, with relationships established between tables using keys. SQL, that is structured query language, is commonly used to interact with relational databases. NoSQL databases are designed to handle unstructured or semi-structured data and provide flexible data models. Cloud databases are hosted database services provided by cloud providers, offering scalability, availability, and managed services. Examples include Amazon RDS, Azure SQL Database, Google Cloud SQL, and managed NoSQL databases like Amazon DynamoDB and Azure Cosmos DB. In-memory databases store data primarily in RAM instead of disk storage, enabling faster data access and processing. They are commonly used for real-time analytics, caching, and high-performance applications. Rate limiters are mechanisms used to control the rate of incoming requests or operations to a system, service, or API. They help prevent abuse, protect against denial of service, DOS, attacks, manage resource utilization, and ensure fair usage of system resources. They help strike a balance between providing access to resources and protecting system integrity and performance. Monitoring system is basically software where system administrator monitor infrastructures such as bandwidth, CPU, routers, switches, etc. This is a critical component of any complex IT infrastructure, providing real-time visibility into the health, performance, and availability of systems, applications, networks, and services. It enables proactive monitoring, rapid incident response, and continuous improvement of systems and applications. A distributed system messaging queue is a fundamental component used in distributed systems architecture to facilitate communication between different components or services asynchronously. They are the essential building blocks for building scalable, reliable, and loosely coupled distributed systems, enabling efficient communication and coordination between components in complex architectures. It acts as a transaction medium between producers and consumers. Messaging queues enable asynchronous communication between components of a distributed system. Popular distributed system messaging queues include Apache Kafka, RabbitMQ, Amazon SQS, Simple Queue Service, Apache ActiveMQ, Google Cloud Pub/Sub, and Microsoft Azure Service Bus. Each messaging queue has its own features, scalability options, and use cases. A distributed unique ID generator is a system that generates unique identifiers across multiple nodes or instances in a distributed environment. These unique identifiers are often used to ensure data consistency, support concurrency control, and provide a reliable way to reference and identify objects or records within a distributed system. In the case of large distributed systems, every moment multiple tasks are occurring, so in order to distinguish it, assign a tag corresponding to every event. Popular distributed unique ID generators include Twitter Snowflake, Instagram ID, UUID, Universally Unique Identifier, and various custom implementations based on algorithms like Flake IDs, UUID v1, or custom sharding schemes. Distributed search is a method of indexing and searching data across multiple nodes or servers in a distributed system. It involves breaking down large datasets into smaller subsets, distributing them across multiple nodes, and coordinating search queries to retrieve relevant results efficiently. The best example is over every website. Crucial information that visitors will seek is put into the search bar. The distributed search enables efficient and scalable search capabilities in distributed systems, allowing organizations to index, search, and retrieve large volumes of data across multiple nodes or servers. It enables real-time search, analytics, and insights, empowering businesses to make informed decisions and extract value from their data. Popular distributed search systems include Apache Solr, Elasticsearch, Apache Lucene, and Amazon Elasticsearch Service. These systems provide scalable, real-time search capabilities for a wide range of use cases, including full-text search, log analysis, monitoring, and content recommendation. Distributed logging services are systems designed to collect, store, and analyze log data generated by multiple components or services within a distributed system with an intent to trace the sequences of events from end to end. These services provide a centralized platform for managing logs across distributed environments, enabling monitoring, troubleshooting, and analysis of system behavior. Popular distributed logging services include Elasticsearch, Fluent, Logstash, Kibana, ElkStack, Splunk, Datadog, Graylog, and AWS CloudWatch Logs. These services offer rich features for log management, analysis, and visualization, catering to a wide range of use cases and environments. A distributed task scheduler is a system that coordinates the execution of tasks across multiple nodes or computing resources in a distributed environment. It manages task scheduling, allocation, execution, monitoring, and coordination to efficiently utilize available resources and optimize task execution. Distributed task schedulers integrate with various computing frameworks, job execution engines, and distributed systems, including Hadoop, Spark, Kubernetes, Apache Mesos, Docker Swarm, and cloud computing platforms. Popular distributed task schedulers include Apache Mesos with Marathon, Apache Yarn, Kubernetes with Kubernetes cron jobs, AWS Batch, Google Cloud Data PROC, and Apache Airflow. These schedulers offer rich features for task scheduling, execution, monitoring, and coordination, catering to diverse use cases and environments. When approaching the design of a distributed system, it's important to follow a structured approach to ensure that all relevant aspects of the system are considered and addressed effectively. Here are the steps you can take. Before starting the design process, it is important to understand the requirements and constraints of the system. This includes gathering information about the problem space, performance requirements, scalability needs, and security concerns. Identify the major components of the system and how they interact with each other. This includes determining the relationships between different components and how they contribute to the overall functionality of the system. Based on the requirements and components, choose the appropriate technology to implement the system. This may involve choosing hardware and software platforms, databases, programming languages, and tools. Define the interface between different components of the system, including APIs, protocols, and data formats. Design the data model for the system, including the schema for the database, the structure of data files, and the data flow between components. Consider scalability and performance implications of the design, including factors such as load balancing, caching, and database optimization. Validate the design by testing the system with realistic data and use cases, and make changes as needed to address any issues that arise. Finally, deploy the system and maintain it over time, including fixing bugs, updating components, and adding new features as needed. We will discuss each topic in detail in the next sessions. Look forward to seeing you in our next one. We hope you've enjoyed the video. Don't forget to like, share, and subscribe. Thank you for tuning in.